Today we will start with vectors, and this is the first chapter of the series of lectures that will be given as learning to the fundamentals of physics. So we start with the fundamental concept, which is vectors, and we will proceed through some of the important concepts that lie there in whichever standard you are in and whichever way you try to learn this subject in detail. So we'll discuss at length what vectors are, what are its properties and the way they are used throughout physics, and the way you can use them when you are solving numericals, and the way you can do some proofs. Okay, so we start with by the definition of a vectors. As you can see over here, the vector or a vector is defined in general by its magnitude as well as its direction, in contrast to scalars, which are defined by magnitude only. For a vector, the fundamental thing to consider is it follows the algebraic laws of vector addition, subtraction, etc. So in general, it is wise to say that a quantity which has magnitude and direction only is not sufficient to be defined itself as a vector. It needs to follow the algebraic rules of vector addition in order to qualify itself. So that's a fundamental point to note. Here are some of the properties which we discussed. We see that equal vectors imply that let's say we have two vectors a and b, and if they satisfy equality, the components are same, as we shall see in the preceding portion. Vectors are either equal or they are parallel, in which the two directions are the same, or one of them is a multiple of the other. There also exists antiparallel vectors, which means that one direction is opposite to that of the other vector, or one direction is a multiple of the other in the opposite direction. Collinear vectors means that two vectors are along the same line, either in the same direction or in the opposite direction, as you see I'm drawing over here. So these are two vectors, they are in the same direction, and these are two vectors which are in the opposite direction. Zero and unit vectors have the usual meaning, which means that zero vector is a null vector, usually defined by 0, and the unit vector is defined by n cap, which you shall see in the following sections, and its magnitude is equal to 1. Polar vectors are a very special class of vectors in which they have a point of application, such as force, displacement, etc. A unit vector is usually defined as the vector itself divided by the magnitude of the vector, as you shall see in this quantity over here. In the top we have the vector itself, and at the bottom it is divided by the magnitude of the vector, and that's how you define the unit vector, which means that a vector of magnitude 1 along the particular direction in which the vector acts. And then you have something which is called axial vector. Axial vector does not lie along the direction in which it works. It is also known as a vector which is out of the plane. So when you rotate, so when you go in a direction which is indicated by this path that I'm marking over here, the vector is usually along the direction which follows. So this is the direction of an axial vector. One example of an axial vector is usually torque, angular momentum, etc. And axis of rotation is seen over here. So in order to define an axial vector, you can clearly see that an axis of rotation is highly essential and a requirement. Now we move on to the orthogonal system of vectors. Oh, I just missed out coplanar vectors. Coplanar vectors are one which lie along the same plane. So let's say if this is a plane as I am drawing over here, so this is these are two vectors and they lie along one plane, and that's how it's known as a coplanar vector. Now we talk about the orthogonal system of vectors. What does orthogonal mean? It means that vectors which lie 90 degrees with each other. So an orthogonal system of vector, as you shall see that it is also known as the rectangular system of coordinates in your language, it is composed of three vectors which are at 90 degrees with each other, and along each direction a unit vector is oriented so that you can define most of your vectors along that way, and you can resolve your vector components along that way. So the first vector, which is known as I cap, that's also known as I hat in some books, that's x vector by mod of x vector, and similarly for j cap and k cap. You shall see that since I cap, j cap, and k cap are unit vectors, their magnitudes are equal to 1, and the magnitudes of them are equal to 1, as I'm writing over here. So apart from the fact that we have defined the orthogonal system of vectors, it is important that we know what are the rules of vector addition, because we have already said that in order to satisfy as a vector, a vector usually needs to have a magnitude, direction, and follow the vector laws of addition and subtraction. And precisely why electric current has a direction, it has a magnitude, but it does not follow laws of vector addition and subtraction, and that's why it's not a vector. So triangular law of vector addition, as you see over here, is given by, let's say if I have this vector OA, as I'm marking with the green color, and then you have a vector which is AB, which you see clearly, and then the final vector, which is the resultant of the two vectors which is acting, is given by OB, and that is the vector R, and that's also known as the resultant. So over here we write R as A plus B in vector notation, or in geometry we write that as OB vector equals to OA plus AB. So one may be curious, how is the magnitude of R found? So we use simple Pythagoras theorem, and we write R square equals to A plus B cos theta square plus B sin theta square, as you can see, and B sin theta is the quantity over here which I am encircling with my green color. And then you find the resultant, which is R square, as I'm marking right now. After a certain calculation, I would highly encourage that you do these calculations all by yourself so that you can get an understanding of how vectors work, and that's how the resultant is obtained from this expression. The angle which the resultant vector subtends with OA is given as alpha, and theta is an angle which the vector A sort of extends with the vector B. So we can see that theta is defined for a problem because OA and AB are two vectors. We know them and we know at what point they're acting. So theta is known for a problem, and that's how you can get alpha given by tan alpha is equal to B sin theta by A plus B cos theta, as you see over here, B sin theta and A plus B cos theta, and that's how you get the value of tan alpha from this expression. From here I want to make some notes that when you are doing vector addition, keep in mind that these vectors are oriented along a particular direction, and you must know the angle theta a priori. In some problems you might be asked to calculate what is the value of theta in the problem. In that case, one of the other parameters might be given. For example, you might be provided with R vector, you might be provided with alpha, and in that way you have to calculate what is the value of theta. Also, you might be given other parameters and one of them might be asked for. So it's a pretty simple arithmetic operation, and it all depends on how you draw the problem and how you see it as from a physics point of view. And then we have parallelogram law of vector addition, which is simply a reiteration of the one that we just discussed over there, and it follows the same results that we just derived and proved, and the results are clearly evident and seen over here. I leave it as an exercise for you to do, but it is as easy as you did in the triangular law of vector addition, following simple geometrical and trigonometrical identities. Now we come to a very important point where we say that a vector may not necessarily be divided only into 2 or 3 components, but it can be resolved into more than one. In fact, a vector can be resolved into infinite components. So if I'm doing something which is called a multi-component decomposition of a single vector, we see that for this vector OE, which is represented by this vector R, can be decomposed into a number of components. So the way by which I'm representing OE, as I'm saying over here, first of all I'm saying OE is equal to R vector, and that can be written as OA vector plus AB plus BC plus CD plus DE. So that's one way of writing it. So you can see that if I go in this direction, and let me take my pen to do over here, let's see. So I'm starting from this point O, and I'm going in this direction, AB, and then BC, and then CD, and then DE, and finally I reach the point because OE is my vector. So R vector can be represented by OA plus AB plus BC plus CD plus DE. Alternatively, I can also write that as OC plus CD plus DE. Also, I can write it as OD plus DE. Also, I can write that as OB plus BC plus CD plus DE. So overall, we get the vector which is OE. But my point was to show that one vector can be resolved into a number of components, although this might not be in the orthogonal or the rectangular system of coordinates that you're considering. Once again, a vector can have infinite components. Now we come to another important point, which is essentially the same as adding of a vector, but in a different way. It is also known as subtraction. And how is it relevant is because it is simply addition of the negative quantity, as you see over here, the way that I'm marking. So a plus minus b, as you see over here, is simply the addition of the negative b vector. Hence, calculating the magnitude won't be an easy deal so far. So won't be difficult. My bad. So in this case, what we do is we replace b with minus b as we see in the problem, and then in the above expression we replace it, or what we can do is we can change cos theta to cos 180 minus theta, because that is indicating the negative direction in which b is acting. So let's say b is acting in one direction, and now b is acting in the other direction. So if this angle is theta, this is definitely 180 minus theta in which it is acting. So that is how we are trying to calculate the angle between A and B. That's one way to do it, or the other way is simply changing the sign of B to minus B. And then we calculate the magnitude of A minus B, and we see that that is equal to A square plus B square minus 2AB cos theta. And as I've already mentioned, you must use only one replacement, either change B to minus B or change cos theta to cos 180 minus theta, right? Then we come to something which is known as a vector resolution, and that is the two-dimensional representation of a vector in an orthogonal coordinate system in which we have an x-axis and a y-axis which are oriented at 90 degrees to each other, as I'm marking over here. So in order to express Rx and Ry along x and y index, we see that R can be represented as Rx I cap plus Ry j cap. This means that Rx is the magnitude of the component of R along the x-axis, and the x-axis has I cap oriented along it. For Ry is the component of R along the y-axis, and that has j cap oriented along that direction. So when we calculate the magnitude of Rx, it is simply R cos theta, and it is written as Rx square plus Ry square cos theta, and R sin theta, which is represented as Rx square plus Ry square into sin theta. Pretty easy, right? That is simply an expression of how to calculate. So I must write here Ry. Something I forgot, but yeah, that's Ry. And then for theta, you have tan theta is equal to Ry by Rx. Theta is equal to tan inverse of Ry by Rx, and that is how you calculate the angle theta, which R extends with the horizontal direction or the x-axis. That's how you calculate theta. So for all practical problems, theta is usually can lie anywhere between the first quadrant, second, third, or fourth. So when you're solving the problem, you must see the signs, and accordingly you must adjust the angles in which the resultant vector subtends with the x-axis. So that is up to the user. When you're doing a problem, you must be careful about what the direction of Ry and Rx is, and accordingly you must choose which quadrant theta must lie. So that's how you sort of do these problems. You approach them from a trigonometric point of view, and make sure that your quadrants are in place. Then we have vector resolution, which is in 3D. And now we say that we are extending one more dimensions, and that's the third axis, and everything else is the same. But here we introduce something which is known as a direction cosines, which is represented by cos alpha, cos beta, and cos gamma, as I'm marking over here. And that is as easy as it is to understand, because let's say if my resultant vector is given as r vector, and this r vector is at an angle alpha with the x-axis, at an angle beta with the y-axis, at an angle gamma with the z-axis. In that case, cos alpha is given as this expression, as you see over here. Cos beta and cos gamma are given subsequently, and they're denoted as L, M, and N. One interesting property of L, M, and N is that a square summation of them is equal to 1, and I think it is pretty easy to prove, because you just square it and add it, and you can see that cos square alpha plus cos square beta plus cos square gamma is equal to 1. And this is a very important identity when it comes to solving problems, as you shall see in the in books. Given that we have now talked about the properties of vectors when it comes to addition, and then we talked about resolution of a vector into several of its components in the orthogonal system. That's how we are trying to analyze the problem. So now we try to analyze how are we treating vectors in terms of multiplication, in terms of operations, in terms of projection. So one of the first artifacts of vector is projection. And projection is as simple as it can go. If you say that, let's say if you have a pole which is at an angle alpha with the horizontal, and you cast some light from top, and you see that there is a shadow. This exactly is the projection of the pole with the ground. So in that way, we have to think about this particular aspect of vectors, and one of them is the scalar product of two vectors, and that is also known as the dot product, and it is defined as the product of the magnitude of two vectors and multiplied with the cos of the angle between them. So when we write the expression for the two vectors a and b, as you see, this is the a vector, this is the b vector, and this is a dot b is equal to ab cos theta. And this is simply the magnitude of the scalar product. And we are saying that this is a scalar product, meaning that it won't have any direction. If when you study in higher courses, you will see that this is an artifact of index notation, where two index finally get contracted out. But for this scope, we just stick to the magnitude, and we say that the properties over here, one of them is commutative, which means that a dot b is equal to b dot a. We will see that this property, as trivial as it may sound, is not true for all forms of vector multiplication. Then you have a distributive property, in which dot product of a vector multiplied with two vectors simply distributes itself as I have shown over here. And then the angle between vectors is represented as the cosine inverse of the respective vector divided by the magnitude of the vectors. Once again, division of vectors is not allowed, but division by magnitudes, it's definitely, because it's a scalar. Okay, so when theta equals to 0, a dot b is equal to ab, since cos theta is equal to 1. And when theta equals to 90 degree, which means when they're orthogonal, it means that a won't have any projection on b, right? So that's so they are known as orthogonal vectors, and the dot product simply vanishes. So an example of dot product which we find in physics and also in everywhere in our daily life is the work done, and is represented as F dot S, which means the force, and it projects on the displacement, or the displacement projects on force. Either way you can go, because you follow this property, which is the commutative property. And then you have phi, which is known as the magnetic flux, which is represented as B dot ds, which you will study when we go to magnetism, and then you will study what is magnetic flux. But the point is, these are also vectors, and these operate in the same way as other scalar quantities. Right. So now that we talked about the scalar product of two vectors, we go into another aspect which is totally different from scalar product, and this is known as the vector product of two vectors, which yields a vector magnitude as well as a direction. So it is defined as the product of magnitude of two vectors with the sign of the angle, and that is very important, sign of the angle between them. So vector direction is perpendicular to the plane containing the original vectors. So when you say the vector direction is perpendicular to the plane, and this word is something which I will highlight, because when you have to calculate a normal or a vector which is at 90 degrees to the surface, this is where the vector product comes in. Because if you calculate this vector A and this vector B, and you do a cross product between them, you will get a vector which lies perpendicular to the surface that I am drawing over here, that contains these two vectors A and B, and the resultant vector is perpendicular to this plane, right? So containing the original vectors and obeying the right hand screw rule. So the right hand screw rule says that if you move your arm from A, okay, not arm, fingers, from A to B, your thumb will point in the direction of C, and that's how you get your direction vector, which is n cap. And that's also known as this is an example of an axial vector which we discussed when we started the description of vectors, and that's how you get the C vector. This is the magnitude of the C vector, and this is the direction. So as I have said, and once again to make you revise through the different concepts, C is always orthogonal to vectors A and B. Even though theta may vary, the theta is the angle between A and B, C is always perpendicular to the plane containing A and B. Property 2, which I said in the previous discussion, that this is not commutative, which means A dot B is not equal to minus B dot A. They have the same magnitudes. As I've mentioned over here, they have the same magnitudes, and this is important, but their directions are opposite. So that means one normal is in one direction and the other normal, when you multiply it in a negative way, so that means if you do B cross A, your normal would be in the reverse direction, although it has the same magnitude. Property 3 is the same as that of the dot product. It means that this is distributive and it follows usual distribution laws. And then we move on to when theta equals to 0 and theta equals to 180, it means that A cross B is equal to 0, which means that A and B are collinear, either in the same direction or in the opposite direction. And if theta equals to 90 degree, which means orthogonal vectors A cross B is equal to 1, because sine 90 is equal to 1. Following the same trend, we see that the orthogonal unit vectors usually have these properties which you see over here, and they follow this clockwise and anti-clockwise sense, which means that if we arrange I, J, and K in an anti-clockwise fashion, we see that I cross J is equal to K, J cross K equals to I, K cross I equals to J, and that follows the anti-clockwise sense. Consequently, if we have the anti-clockwise, so first we did the anti-clockwise and then we are doing the clockwise, we see that J cross I is equal to minus K and K cross J is equal to minus I, and subsequently. The whole point of discussing is the direction of your assumption. The direction in which you are going is very important when you are talking about vector products, because that decides which direction your final vector is or your normal vector is. So for two vectors A and B, we see that A cross B is equal to IJK and AX, AY, AJ, AZ, and BX, BY, BZ, and this thing is known as the determinant. And this will help you to calculate the resultant vector of A cross B, including the directions. So this determinant helps you to do that. And if you know some matrix algebra from your classes, from your math courses, from your math classes, this will definitely help you to write the expression in the final form and give you an understanding how the normal is oriented, what is the magnitude of the normal when you do a vector cross product. So we see that AX, AY, AZ, BX, BY, BZ are the components of A and B respectively in the 3D orthogonal coordinate system. I highly encourage you derive these things and try to convince yourself that A cross B essentially gives this expression so that you can calculate problems when you go into more complex topics. As I've mentioned already, torque, angular momentum, velocity, these are all examples of axial vectors or vectors which are obtained from a cross product operation. Our final topic for the day is Lamy's theorem. So Lamy's theorem states that if we have three vectors A, B, and C, and the angle between the vectors A and B is 180 minus gamma, as I mentioned over here, the angle between B and C is 180 minus alpha, and between C and A is 180 minus beta, while the internal angles are B, gamma, and alpha. We say that sine alpha by A equals to sine beta by B equals to sine gamma by C. So this is a property which was given by Lamy and has come down the ages to be one of the most powerful identities and operations that you can utilize in order to calculate the angle between two vectors. In that case, the vectors can be forces as well, and their corresponding lengths of the triangle, which means the magnitude of the vector. So this is a very important property which you shall shortly see over here, and the proof that I'm giving over here. So let's say that A plus B plus C is equal to 0, which means all sides are in order, and A plus B is equal to minus C, because I can shift the C to the other side. And then if I do a vector product of A on these two sides, we say that this identity is finally obtained. Once again, I would tell you to do this proof because this is a very simple one, but then its understanding is really important. So A cross B is equal to C cross A, as you see from this identity. Similarly, multiplying both sides with this equation, this is a base equation, and first of all I multiply this with A cross, so that means I do a vector product with A, and then I do a vector product with B, and then I obtain these two expressions, which is given in 2 and 3. So 2 and 3 gives me this identity, and if I try to write it down, so as I said, the magnitude of the cross product is given as the magnitude of the individual vectors multiplied with the sine of the angle between them. So if I carry out this expression and then I divide all sides with the mod of these three vectors, we get this final identity, which is written over here. So essentially, Lamy's theorem is an artifact of a coplanar system of vectors, and these three vectors add up to 0, and then we establish the identity based on a vector cross product magnitude operation, which is not very difficult to understand, but I would highly suggest that you do these proofs by yourself and try to get an understanding and intuitive feeling about how vectors operate in general. So now I'll discuss some of the trivia about vector in general. So I have already discussed these things previously, but this is just a revision of before I finish off the chapter and I send out this video so that you can watch it. So a vector can have infinite components. A vector can be resolved into as many components as it can, and we need not always stick to the rectangular system of coordinates. For your problems in the book, you will be given numericals which obey the rectangular system of coordinates because it is easier to solve in a calculator or a paper pencil, or it's easier to visualize. But in general, a vector can have infinite components. Division of vectors is not allowed because here we are talking about division by magnitudes, directions, and that is not allowed in vector algebra. Minimum number of collinear vectors which gives the resultant vector is equal to 0 is 2. Minimum number of coplanar vectors whose R is 0, which means the resultant is 0, is 3, and the minimum number of non-coplanar vectors whose resultant is 0 is 4. This is to say that, let's say if you have two vectors which are in line with each other, then the minimum number of vectors that you need so that your final resultant is 0 is 2. If your vectors lie on a plane, as you saw in Lamy's theorem, a plus b plus c is equal to 0. That means you need at least 3 vectors so that a set of planar vectors results to 0. And let's say if you don't have a planar system, if you have vectors which are skewed, which means they don't lie in a plane, essentially in that case you need at least 4 vectors so that the resultant is 0. So there is another thing which is important to realize, that the components of a vector can have magnitude greater than that of the vector itself. However, the above is not true when you're working for rectangular, Cartesian, or orthogonal system, which is your standard x, y, z coordinate system, right? Now, another important thing which one should always remember, that let's say if we are talking about two vectors which are equal to each other, in that case a equals to b, the individual components of the vectors are also same, which means that ax equals to bx, ay equals to by, az equals to bz, and that holds true for all forms of vectors. Let's say if modulus of a is equal to modulus of b, or in this language you should say that magnitude of a is equal to magnitude of b, in that case you have this identity as same, which means the magnitude of the individual components of the vector, the square of the components of the vectors, and doing a square root of them, and that is equal. That's how the magnitude of two vectors can be same. And now we talk about the final portion, which is a little interesting, which says that the projection of a vector a in the direction of b is given as a dot b by b vector. So let's draw this example and see how this thing is trying to understand. So these are two vectors, as you can see over here, and this is a vector, this is b vector, and then I do a projection of this vector over here, right? And then we are saying that the projection of the vector a onto this vector, which is b, what is it? What is the value, right? So if I expand this expression, we say that this is a vector, b, and then you have cos of the angle between them, let's just specify it as b, and then you have b, right? So we see that that is equal to a cos theta. So let's say if I have a, and if I'm trying to resolve a into two components, so this angle, let's choose a different color for that. This is a sine of theta, and this is a cos theta. So these two are same, and that's what it means when I'm saying projection of a vector A in the direction of B. So this is the end of the chapter 1, which talks about vectors. If you have any questions, I will give the details at the description of the video. So stay safe and see you for the next class.